Hi and Assalamualaikum. We are from Group 16 of AS120 and today we are going to present about gas chromatography.
Before we start, let me introduce our team members. My name is Putri Sabrina. My other team member is Nur Amna Najwa, Nur Fazila Tasha, and one is Mahani Shamimi.
Production part. Gas chromatography is an analytical technique used to separate volatile compounds based on their difference in boiling point and interaction with the stationary phase. In GC, a vaporized sample is carried by an inert carrier gas through a column where components are separated and detected as peaks with specific retention times. Retention time is an important parameter for identifying compounds in standard mixture and unknown samples. In this experiment, GC is used to determine the retention time of an butanol and 2-propanol, identifying mixture component and study the effect of temperature on retention time and peak resolution, highlighting the relevance of GC theory in practical chemical analysis. For objective part, first is to determine the retention time of N-butanol and 2-propanol. Second is to identify the components present in a standard mixture based on the retention time. Lastly, to determine the effect of temperature on retention time and resolution peaks.
To understand gas chromatography, we first have to look at the racetrack where everything happens, the column and the carrier gas. The column is the heart of the system. Its job is to take complex mixture and separate it into individual components. It does this through differential partitioning. Imagine a coating inside the column called the stationary phase. As molecules travel through, those with a weak affinity move fast, while those with a strong affinity stick to the coating and move slower. But they can't move alone. They need the carrier gas, which acts as the transport vehicle. The gas must be inert so it doesn't react with the sample. We control the separation by adjusting temperature, the length of the column, and choosing the coating polarity that matches our sample type. The injector is the gatekeeper of the system. It is responsible for turning a liquid sample into a gas without losing the precision we need for analysis. The sample injection system has a few vital jobs. The first one is vaporization. It's heated so that the moment your liquid sample hits it, it flashes into a gas. Because GC is used for quantitative analysis, volume control is key. We use two main modes. The first one is split injection. This is used for high concentration samples. It vents most of the sample out so we don't flood the column we just talked about. The second one is splitless injection. This is for trace level analysis, where we want every single molecule of the sample to reach the column for maximum sensitivity. If the column is the racetrack, the detector is the finish line camera that records exactly who finished the race and when. The detector converts the chemical separation into a digital signal. An ideal detector is highly sensitive, stable, and has a wide temperature range, often up to 400 degrees Celsius. Depending on our goal, we use different types. The first one is FID. The most common for organics, it uses a flame to ionize molecules. Next is TCD, a universal detector that measures changes in thermal conductivity. And the last one is ECD, a specialized tool for detecting electronegative elements like halogens. By the time the sample hits the detector, we have successfully turned a messy mixture into a clear, actionable data.
In this result, I will explain about the 2-propanol and N-butanol. For the 2-propanol, the retention time is 2.724 minutes that correspond to peak 1 of standard mixture, and the peak high is 2.82. For the N-butanol, the retention time is 6.043 minutes that correspond to peak 3 and 4 of standard mixture and have a peak high of 6,952.48. This result indicates that when the temperature increases, it will reduce retention time. So propanol will elute first before butanol. They indicate temperature, not change elution order. For the 2-propanol, it have a shorter carbon change, lower boiling point, which is 97 degrees, and also have a higher volatility. So it will elute first before N-butanol. For the N-butanol, it have a longer carbon change, higher boiling point, which is 117 degrees, and also have a lower volatility. Since it have a larger peak height, so indicate higher concentration. So it will elute later after the 2-propanol. Next, we have 3 standard mixture. First is the 70 degrees, second is 100 degrees Celsius, and the third one is 140 degrees Celsius. For the standard mixture 1, the peak 1 is known as 2-propanol, which is have retention time of 2.692 minutes, and the peak 3 known as N-butanol for the retention time of 5.903 minutes. For the standard mixture 2, for the 100 degrees Celsius, the peak 1 known as 2-propanol with the retention time of 2.269 minutes, and the peak 4 known as N-butanol, which is the retention time is 3.294 minutes. And the standard mixture 3, for 140 degrees Celsius, the peak 1 is known as 2-propanol, which have retention time of 1.952 minutes, and the peak 2 known as N-butanol, which have retention time of 2.225 minutes. This result indicate that when temperature increase, retention time will be decreased due to increase analyte volatility. And the retention time will change with temperature, so elution order will remain the same. Next is the result of RS. For the first one is 2-propanol. The RS is 18.98. For the N-butanol, the RS is 23.08. And the standard mixture 1, which is 70 degrees, the RS have 2 since it have a 3 peak. So the first is 5.47 and the second one is 29.47. Next, the RS result for standard mixture 2, 400 degrees Celsius. We have a 3 result of RS since it have a 3 peak. So for the first one is 3.11, the second one is 5.13, and the third one is 14.21. For the standard mixture 3, for the 140 degrees Celsius, the RS result have 2 since it have a 3 peak. So for the first one is 6.57 and the second one is 15.59.
This discussion section is based on the experimental data provided for the gas chromatography. There is a 2 analysis of 2-propanol and also N-butanol. The analysis included 5 distinct chromatograms used to identify a component and also to evaluate the temperature effect. First, we have individual standard, which is 2-propanol. It is analyzed at 70 degrees to establish its characteristic retention time. Second, we have individual standard, which is N-butanol, to analyze at 70 degrees to establish its characteristic and also retention time. Third, we have a standard mixture at 70 degrees used to identify the component in a combined sample under a baseline condition. Fourth, we have standard mixture at 100 degrees Celsius used to observe the effect of moderate temperature increases. And lastly, we have a standard mixture at 104 degrees used to observe the effect of high temperature and also separation. To identify the peaks in the mixture, we will compare the retention time of the individual standard with the peaks produced by the mixture at the same temperature, which is 70 degrees Celsius. For the 2-propanol, the pure 2-propanol is exhibit a retention time of 2.724 minutes. In the standard mixture at 70 degrees, peak 1 will appear at 2.692 minutes. Due to the approximate of this value, peak 1 is identified as 2-propanol. For the N-butanol, the pure N-butanol sample exhibit a retention time of 6.043 minutes. In the standard mixture of 70 degrees, peak 3 is appeared at 5.903 minutes. Therefore, peak 3 is identified as N-butanol. The retention time matching of each substance has a unique retention time under specific condition. The first peak in the mixture, which is 2.692 minutes, closely match the 2-propanol standard, while the second peak, 5.903 minutes, matches the N-butanol standard. For the elution order, 2-propanol will elute first because it has a lower boiling point, which is 82.6 degree compared to N-butanol, which is 170.7 degree, meaning it spends more time in the mobile gas phase. As the column temperature increases, the retention times for both compounds decrease significantly. At 70 degrees Celsius, the last peak, N-butanol, eluted at 5.903 minutes. At 100 degrees, the last peak eluted at 3.294 minutes, and lastly, at 140 degrees, the last peak eluted at 2.225 minutes. As the increasing temperature, the vapor pressure of the analyte will causing them to move through the column faster, which will reduce the total analysis time. For the effect on a peak resolution, the resolution is referred to how well the two peaks are separated from each other. First, a reducing temperature, which is 70 degrees, the peaks will be spread far apart, difference of 3.21 minutes, providing a high resolution and clear separation. However, the peaks are broader. But if increasing the temperature at 140 degrees, the peak will elute very closely together, difference only 0.27 minutes, while the peaks are narrower and sharper. The resolution will be decreases, rising peak overlap if the temperature is too high.
In conclusion, this experiment, we were able to determine the retention times of different compounds. The retention time of N-butanol was 6.043 minutes, while 2-propanol was 2.724 minutes. This allowed us to identify the components present in the mixture based on their retention times. We also observed the effect of temperature on retention time and resolution. As the temperature increased, the retention time became higher and the resolution also improved. Beyond this experiment, gas chromatography is widely used in pharmaceuticals, food analysis, environmental monitoring, and forensic science for the identification and analysis of volatile compounds.
So here are the references that were used in the making of this presentation slide.
That's all from us. Thank you for watching.